Hello everyone. So now we will discuss conformers. So across carbon carbon or across between two atom, that single bond when it's rotate due to that different orientations of that molecules occurs, that is called conformers. So let's start. First conformer definition, that isomer which having same molecular formula and a structural formula, different arrangement of atoms or group of atoms in a space, and they are intra-convertible, they are called conformers. Now in nature, in surrounding, each atom or molecule having energy 80 kilojoule per mole, that surrounding energy provided to each molecule, how much? 80 kilojoule per mole. For rotation of that carbon carbon bond, it can rotate. For that energy is required 12 kilojoule per mole only. Hence, that nature already provided sufficient energy, due to that carbon carbon bond will rotate. But carbon double bond carbon, for that rotational energy is 260 kilojoule per mole. Energy is provided by nature is 80 kilojoule per mole. So carbon double bond carbon cannot rotate, means its rotational energy barrier is much higher than activation energy which is provided by surrounding. So here you can see in this picture, like here, in this single bond is rotating, so due to that in S space its molecular formula and structural formula is same, but different orientation in a space it is coming, and they are intra convertible, they are only called conformers. But here you can see that double bond, this double bond having that bond energy or rotational energy barrier is higher than the activation energy, so it cannot rotate. Similarly here triple bond also cannot rotate. Clear? So on behalf of this, next, moving further, so that let's suppose for example butane is there. So butane, for that rotational energy is 12 kilojoule per mole, but surrounding energy is provided 80 kilojoule per mole, so hence it can rotate. So it is called free rotation. They are intra convertible, they are conformational isomer, they remains in dynamic equilibrium because always it is rotating. They are also called rotamers, and they are not true isomers because they are infinite orientation such like that possible. Now that 3D, that any molecule is in a space if it is 3D, so to represent in 2D, there are some ways we can represent. First representation is wedge dash representation, that 3D molecule we can represent in 2D. Like ethane is sp3 hybridized carbon, so that we are representing in 2D. So you can see here carbon, in that this line is called dash and this one is wedge. So dash, wedge, and this carbon and hydrogen is in plane, this line is also in plane, this carbon and hydrogen is in plane, this hydrogen is above the plane, this hydrogen is below the plane. Similarly, this hydrogen is above the plane, this hydrogen is below the plane. Suppose observer is here and this observer is seeing this carbon. On behalf of that, next representation which we can do by the help of wedge dash representation, Sohor's projection. Here you can see that this carbon can rotate, conformer. So as it will rotate by angle, minimum angle 60 degree, then what will happen? This inner hydrogen will go backward and this hydrogen will come forward, and this above hydrogen will become in plane. Once again, as we will rotate, so this hydrogen which is above the plane will go to that in the plane, and this hydrogen which is below the plane, it will go below the only plane like this, and this hydrogen will come above the plane, like when we will rotate like this, means like this. So due to that, this hydrogen will come above the plane. So this is representation, wedge dash representation of ethane by rotating minimum angle 60 degree. Similarly, you can see on behalf of this is Sauer's representation. So Sauer's representation is what? This is also 3D molecules in 2D representation. So suppose observer is here. So for this observer, right hand side one hydrogen and left hand side one hydrogen is there. So right hand side, left hand side one hydrogen and one hydrogen is above. Let's suppose this carbon is front carbon for the observer. So this carbon will be back carbon. And here also right hand side one hydrogen and left hand side one hydrogen and above one hydrogen. So you can see that this hydrogen is covered by this hydrogen. Similarly, this hydrogen is covered by this hydrogen. And similarly, this hydrogen is covered by this hydrogen. So this structure is called eclipse structure of Sauer's projection. If suppose again here this is conformer, so it will rotate by 180 degree. So if it will rotate by 180 degree, so this two hydrogen will go up, above and below, means left and right, and this hydrogen will come down. So now here you can see this hydrogen and this hydrogen is like empty almost. So this is called a staggered conformers. Whenever it is covered by this respective back carbon atoms, then it is called eclipse. If it is not covered, then it is a staggered. On behalf of this Sauer's projection, now we will draw Newman projection. So in Newman also you can see that here observer is there. So this observer is seeing this carbon is a front carbon. And right hand side hydrogen, left hand side hydrogen and one hydrogen is connected to this front carbon. Similarly, all hydrogen are in fact connected. This hydrogen is up. Similarly, this hydrogen is up and two hydrogen left and right. This is back carbon. So on behalf of that, when we will draw its Newman projection, you can see this front carbon, this hydrogen, similarly this hydrogen and this hydrogen. And for back carbon, all those are since eclipse, so covered by each other. So little bit slightly we will draw this side. So this is back carbon with that hydrogen, again left and right and left. So this is eclipse projection. And another one which we rotated by 180 degree, this one. So again front carbon is same, back carbon having that how much angle with respect to each other, 180 degree. So here what will happen, that front carbon is same, back carbon is rotated by 180 degree, means this hydrogen came here and this hydrogen came here, and similarly this hydrogen came here. So this is a staggered of after rotating 180 degree. So this is eclipse in Newman projection and this is a staggered. You can visualize this one also like here. This one is your Sauer's representation, whereas this one is its Newman projection. So on behalf of that, now we will move on after understanding 3D molecules representation in 2D. First one we discuss that dash wedge representation. Next after that we discuss that Sauer's representation, and then after we discuss Newman projection. Now on behalf of that general example we will consider. Let's suppose this is CH2 single bond and here ZZ. So what will happen, even this single bond also will rotate and this one also will rotate. So we are considering with respect to this one is front carbon and this one is back carbon. So front and back carbon, first one is, let's suppose this is eclipse. So Z is covered by Z, hydrogen is covered, and this side hydrogen is covered. Angle between this both Z, similarly hydrogens, is 0. So this is fully eclipse. Now let's suppose with respect to front carbon, if back carbon is rotated by 60 degree. So if back carbon is rotated by 60 degree, then what will be? Z will be here. Now this is a staggered. This staggered conformers, when angle is in between this, it's 60 degree, ZZ, then it is called gauche conformation. This is called gauche. Again, if rotated by 60 degree, then Z will come here. This Z will come here. So this is called partial eclipse. This is a fully eclipse because Z and Z together. Now here Z and H. So this is called partial eclipse. Now again rotated by 60 degrees. So Z came here. Now you can see both Z. This is again a staggered conformers. In that you can see this Z and this Z both are anti to each other. So this is called anti-conformations. Again rotated by 60 degrees. So Z and H eclipse with each other, but it is partial eclipse. Again rotated by 60 degrees. So Z is here. Now this both you can see same again together like here. So it is called gauche conformation. And again by 60, then it will be fully eclipse. So from here we can see that here ZZ repulsion is more because both are bulky group together. So fully eclipse is highly unstable, and partially eclipse is somewhat stable relatively. In gauche it is relatively more stable. Maximum stable is which one? Anti. In that you can see both bulky groups are anti to each other, hence their stability is more. So according to this stability, which one is more stable? Anti-conformer is more stable. Then after gauche, so this anti and gauche you can see here, anti and gauche. This both are staggered conformers, two different orientation. Anti in that both are at 180 degree. So anti is more stable. Then after gauche, this both are your staggered. And then after partially eclipse, and then after fully eclipse. So fully eclipse is the least stable. So higher the stability, less will be its potential energy. So let's draw its graph also. One thing you can see here that this 1 and 7, this both are same. But 2 and 6 both are gauche. Both are mirror image of each other. If we'll keep here mirror, so its mirror image will be this gauche. Similarly 3 and 5. So 3 and 5, this one 3 and this one 5. This both are also mirror image of each other. Clear? Now moving further, here you can see potential energy versus there. So here which one is the most stable? NT. So NT most stable, so its potential energy will be minimum. Then after gauche, then after partial eclipse and full eclipse. So on behalf of angle, that minimum angle we took 60 degree. So on behalf of 60 degree, that first it was at 0 degree it is fully eclipse. After that it is that gauche, and then after again next 60 degree it became partial eclipse. Again after that it became NT. Then after again gauche. Partial eclipse, then after gauche, and then after again at 360 it became full eclipse. So here you can see this one is maximum, that this one is the that lowest value, means here potential energy is minimum, so its stability is maximum. So this point is absolute minima, whereas these two gauche are local minima. So total number of conformers, how many possible between carbon-carbon single bond? Infinite possible. At 0 degree, 0.1 degree, 0.2 degree, like that we can infinite conformations we can create. That's why it is not true isomer. But how many total stable conformers are possible here? Either 3 or 1. When it will be 1? When Z will be same, then only it will be a staggered and eclipse. But when Z will be different, then it will have a staggered having two part. It will have NT and gauche, and eclipse also will have two part, partially eclipse and full eclipse. So on behalf of that, it will have three local minima, two local minima and one absolute minima, means three stable conformer will be there. So that's why here total stable conformer less than or equal to 3. If Z will be different, then 1 NT and 2 gauche. If Z will be same, then only it will have one staggered will be stable. Moving further, now you can see here rotational barrier. If z size will be more, so due to that rotational barrier will be relatively, means rotational energy barrier will be more, means its rotation will be difficult. So rotational energy barrier, that energy difference between most stable versus least stable conformer. So here you can see rotational energy barrier, this one. So this one is the rotational energy barrier from least stable to that, this one, absolute minimum. So in between this difference, energy difference is called rotational energy barrier. So if more the bulkier, if jet size will be more and more, rotational energy barrier will be more, means it's difficult to rotate that across carbon, single bond carbon. So moving further now, that some of the related points we will discuss. So here you can see order of rotational energy barrier. In N-butane, rotational energy barrier is more, means rotation will be not easier than after propane and then after ethane. So in ethane, relatively rotational energy barrier is less, means relatively rotation will be more easier. So here you can see more the number of carbon atoms, more steric hindrance, more will be rotational energy barrier, hence its rotation will be not that effective. Now coming here, dihedral angle. So dihedral angle is what? Angle between this front carbon or back carbon, in between ZZ, whatever the angle is there, that is called dihedral angle. Mean between the two plane, this two valency having whatever that angle is only called dihedral angle. So angle between two specific group in Newman projection is only called dihedral angle. Like here in Newman projection, like two specific position here, this two specific position. In this you can see angle difference is how much? 60 degree. So means angle between this Z and Z is 60 degree. So this is only called dihedral angle. So dihedral angle, if theta is 0, then it is of course fully eclipsed. If theta is 60 degree, then it is gauche. If theta is 120, partially eclipsed, and so on and so forth. Next, for any compound which is showing conformer across single bond, that will have two types. One will be a stable conformer and one will be unstable conformer. So a stable conformer is a staggered and unstable is eclipse. If suppose here Z is hydrogen, means Z will be same, then only it will have a staggered and eclipse. But if Z is not hydrogen, some different atom or group of atom, then a staggered will have two types, anti and gauche. In that you know anti is more stable than gauche. And in eclipse, partially eclipse is more stable than fully eclipse. So eclipse having also two types. Third point, that van der Waal strain. So van der Waal strain is what? That whatever the atom or group of atoms are there, in that whatever due to that steric hindrance and due to that steric hindrance, they are unstable. So like you can see fully eclipse, in that steric hindrance is more, means van der Waal strain is more, due to that it is less stable. But coming to in gauche you can see comparatively that in bulky group distance increases. So due to that gauche is relatively more stable than that fully eclipse. So that van der Waal strain will be where maximum. If van der Waal strain is maximum, means its stability is minimum. Same we discuss in potential energy curve also. So here you can see in fully eclipse, van der Waal strain means this attached atom or group of atom having more steric hindrance, due to that van der Waal strain is more. So in fully eclipse, van der Waal strain is maximum, then after partially eclipse, then after gauche, in anti it is least, because both are anti to each other. Now coming to one another strain, this is torsional strain. Many times students are getting confused, but torsional strain is irrespective of whatever here atom or group of atom is attached. Torsional strain is just a strain that electron density here, that this bond having electron density and this bond also having electron density. So this bond pair repulsion is called torsional strain. Clear? It is irrespective of whatever here that group of atom is there, irrespective of that, torsional strain is just bond pair repulsion. So in eclipse, whatsoever eclipse there, whatsoever means either partially or fully eclipse, always torsional strain will be same in that. Compared to a staggered, in that you can see as a distance increases, so their bond pair repulsion is relatively less. So always torsional strain will be higher in eclipse as compared to a staggered. And if Z is not same, then torsional strain will be in this fully eclipse, and partially eclipse it will be same only, because irrespective of group of atom, and gauche and NT also, that torsional strain will be same because it is irrespective of group of atoms. So here you can see torsional strain is independent from the type of atom or group of atom. Now last one point, that is skew conformers. Skew conformers, since we decided while drawing that potential energy graph, we that rotated across carbon by angle 60 degree, that minimum angle, but that angle could be any. So if that angle is greater than 0 and less than 60 or any other angle, so that such all those positions are called skew conformers. That a specific angle is 0, 60, then after means 60 multiple 60, then after 120, 180, that are the specific angles. At that we will get some some named conformers like NT, gauche, partially eclipse like that. But at any angle also conformer do exist, so that all those conformers are called skew conformers. Now a staggered conformer is more stable than eclipse. So generally that concept is what? That a staggered is more stable than eclipse, because in a staggered van der Waals strain is less, and along with that torsional strain is also less. That's why it is more stable. But experimentally, contribution of van der Waals and torsional strains is only 15%. So remaining 85% is some other factor is there. Due to that, a staggered is more stable than eclipse. What is that reason? So here you can try to understand. Let's suppose this one is your staggered conformer. So in a staggered you can see Z is here and this Z is here, means it is NT. So this Z having this bond pair means sigma field, and similarly this carbon and Z. So this is also sigma field. So if it is sigma field, so its sigma a star will be NT to it. So this sigma star is vacant. In that, some electrons are moving from high electron density to low electron density, sigma field to sigma star. Similarly, you can see here also this is carbon and Z, this is sigma field, and this sigma star is here. So again electrons are moving from high to low. So due to that movement of electrons, its energy again further decreasing, and due to that a staggered is more stable than a staggered is more stable than eclipse. Even though it's van der Waals and torsional strain contribution, yes, that is supporting factor, but that is not altogether is the main factor. So here which one is that in a staggered, due to sigma field is that electrons moving to sigma star vacant, due to that a staggered is more stable than eclipse. Whereas you can see in eclipse, if this is sigma field, so its sigma star is vacant here, and similarly it's also sigma star vacant is here. So now electron movement is here not happening, so its stability not that much. So this is the main reason. Next, here it is asking draw the most stable conformers. So most stable conformers, generally we have what notion, that NT is more stable than that gauche, and then after gauche is more stable than partially eclipse, and then after fully eclipse is the least stable. So here also, let's suppose this is glycol, bicdiol or pinacol is there. So to draw its structure, we will think it's anti, but related to anti, gauche is more stable due to intra hydrogen bonding. So whenever that hydrogen bonding is possible, hydrogen bonding will happen, hydrogen will combine, hydrogen will form hydrogen bonding with only with fluorine, oxygen and nitrogen. So here hydrogen bonding is possible, hence gauche is more stable over Nt. Moving further, now you can see here also, here hydrogen bonding is not happening. Here that charge species are there, so it having electrostatic attraction. So again gauche will have more interaction, due to that it is more stable. Here coming to this set of acid, that carboxylic acid. So again here it having hydrogen bonding, so it is more stable. But here since hydrogen bonding is not there, or same charge, it is negative and negative. So due to that negative, it will have repulsion. So now instead of that gauche, here Nt is more stable. Clear? Next, moving further, here you can see this two example, that this two, that here this one molecule where conformer happening around carbon, single bond carbon, and here also conformer happening. In this, gauche is more stable. Here also you can see this is gauche is more stable. Here also gauche is more stable. So what is the main reason that gauche is more stable? Here no interaction happening between charge, no interaction happening with hydrogen bonding. Still here we are considering gauche only as a that more stable than Nt. So what is the main reason? So main reason is again here, like there we discussed that staggered is more stable than Eclipsed. Main reason is that sigma filled electrons are moving to sigma star vacant of back carbon, and similarly back carbon sigma filled is moving to sigma star of front carbon. Similarly here also you can see why gauche is more stable than Nt, only for this two example. So let's suppose this is carbon and this one is carbon and fluorine bond, so its vacant orbital is here. Similarly this one is carbon and fluorine, so this one is gauche, and here it's carbon and hydrogen. So carbon and hydrogen electrons are moving to high electron density to low electron density. But if we'll take its Nt, means here this fluorine and this fluorine both are Nt to each other. So sigma vacant, in that this electron will not move, since here carbon hydrogen bond, in that electrons easily moved because carbon is relatively less electronegative, but fluorine is very highly electronegative. So due to that this electrons are tightly held, means now electron will not move from high to low. So here due to that region, that gauche, in that electrons are moving, carbon hydrogen electrons are moving to sigma star vacant, and due to that delocalization electrons, that gauche is more stable than Nt. Similarly we can also say for that here also there's all those examples where that here charge is, due to charge interaction gauche is became more stable, or here that due to hydrogen bonding gauche became more stable. Again its percentage in contribution of stability is very less. Main factor is which one? That carbon hydrogen bond. Yes, this one is the main factor, that carbon hydrogen bond electrons are moving to sigma star vacant. So this is the main factor. Again hydrogen bonding is also one factor, but that one is the not main factor. If that could be a main factor, then here Nt should be more stable. Understood? Next, moving further, total number of conformers we have to draw. So let's suppose this is ethane. So in ethane, if it is front carbon, so this is back carbon. So front carbon having 3 hydrogen, back carbon also having 3 hydrogen. So all three move that a stable number or a stable conformers. So stable conformers what? Either gauche or Nt. So here gauche and Nt not possible because all are same only. So relatively, so only one conformer is stable. Here also CH3 and along with that CCl3. So CH3, that 3 hydrogen front carbon, and chlorine is here. This chlorine will rotate by again that from this to that. Let's suppose this is gauche, so then it will be NT. So here gauche NT not possible, so again only one conformer. Now coming to this example, here you can see carbon single bond carbon. So here this will be also conformer, here this will be also conformer, here this will be also conformer. So all will rotate. So let's suppose this is front carbon and this is back carbon. Similarly, this is front carbon and this is back carbon. Front carbon, back carbon. So with respect to this, if suppose this front carbon hydrogen CH3 and CH3 is fixed, so back carbon hydrogen even we will rotate, because back carbon all three atoms are same, so only one is possible, staggered. Staggered, two types possible, that is gauche and NT. That is not possible here, because back hydrogen, even front carbon, all three atom or group of atoms may be different, but that one we are keeping fixed. And back carbon, all three atoms we are rotating by to get from that gauche to NT, but still it will be same only, because here all three atoms are same, hydrogen. Similarly with this respect to this also, here also hydrogen and here also hydrogen. So this line also will give that most stable, staggered only. Here also staggered only, and here also staggered. So with respect to this carbon, when this line will be staggered, when this line will be also staggered, and when this line will be also staggered, that conformer will be more stable. Understood? It's not like that with respect to this carbon, this line is staggered and this line is eclipsed and this line is staggered, then that is not relatively stable, but that is not most stable. Similarly, moving further, here again carbon single bond carbon will show conformer, carbon single bond will show conformer, carbon single. So three lines are there, three single bonds, so three conformers possible. So again, let's suppose this is the front carbon, so two hydrogen and one ethyl group is there, and this side back carbon having again all three hydrogen, so it will be staggered only. Similarly here also this, so two hydrogen and CH3, and this side two hydrogen and CH3. Now it will be different. Why? Because if suppose this is the front carbon, so front carbon is fixed, means it's two hydrogen and CH3 is fixed, but here it having two CH2, two H2 and one CH3. So now as we will change, so if CH3 is angle between them is 60 degree, then it will be gauche, and if it is angle is 180 degree, then it will be NT. So a stable conformer means with respect to this single bond only a staggered possible. With respect to this also, since here also CH3 means all three hydrogen, so this will be also a staggered possible. But here with respect to this single bond, gauche also possible, NT also possible, and again gauche possible. Means total how many conformers possible with respect to this? 3. So in this 3 you can see here this CH3 and CH3. So this is what? This is with respect to this carbon, this one is staggered. With respect to back carbon and this carbon is staggered, and this two carbon with respect to this position is gauche. So this is stable. Next, this one is most stable, and then after another one mirror image of gauche, this one. In that we can see that this one, its dipole moment cancelling each other, so it is non-polar, whereas this is polar and this one is polar. So if it is asking question that total stable conformers, so how many total stable conformers? 3. And total stable conformers with that polarity, polar nature, so 2 are polar and 1 is non-polar. Similarly here we can see also that How many carbon single bond there? One. So this will also show conformer. Here this will also show conformer. Here this one also will show conformer. Here this one also will show conformer. So like here carbon, so let's suppose this is front carbon, so back carbon, all three hydrogen are same, so it will be staggered. Similarly this one also staggered, and this one also staggered. Now we need to study this one. So front carbon, let's suppose we are taking this one, so back carbon is this. Any we can take front and back. If front we are taking, that will be fixed. So front carbon is this one, so it having what? CH3, CH3 and H. This one is fixed. So CH3, CH3, H we fixed. Now back carbon will rotate. So back carbon is what? Having two hydrogen and CH3. So having back carbon having two hydrogen and CH3. So you can see this one is one possibility. Next, again we will rotate. If we will rotate by 60 degree, then it will be eclipse. So again we will rotate by 120. So by rotating 120, next we will get this one, and again we will rotate by 120. In that we cannot say that NT and gauche, because CH3 is there, here also CH3 and like that. So we cannot say, but yes, these three are possible stable conformers. Yes, with respect to this carbon, back carbon and this carbon also should be staggered. Front carbon and this CH3 also should be staggered, and this also should be staggered. Along with that, overall this conformers, that is the stable one. Similarly here also and here also, that back carbon, front carbon and front carbon, this should be staggered. Along with that, this conformer between this carbon, this is also stable, and similarly this one. So total how many conformer? 3, and in that all 3 are polar in nature. Now we will discuss gauche effect. So gauche effect is what? Whenever that lone pair containing atom or group of atom is coming, then it will show gauche effect. What is meaning of gauche effect? See here, this is the bond pair. So in bond pair you can see that two orbitals are overlapping each other, means it will occupy more space. Whereas lone pair, in that only one orbital will be there, hybridized orbital, means it will occupy less space. So let's suppose this molecule is there, CH3 CH2 OH. In that this oxygen having two lone pair. So this two oxygen lone pair is here, and along with that hydrogen. This one we are keeping fixed. Now with respect to this, single bond will rotate due to activation energy. So here this one is CH3, and along with that back carbon, and it having two hydrogen also, CH3 and two hydrogen. Now we will rotate by 120. So by rotating 120, stable conformers again we are doing. So by rotating 120, what it will be? This CH3 will come here, and this hydrogen will go there, and this hydrogen will go there. So this is, again we will rotate by 120. So this CH3 by 60 it will come here. By rotating 120, CH3 will come here. So this CH3 is here, then after hydrogen here, and this hydrogen. Now we can see that since lone pair is occupying less space, but bond pair occupy more space, and along with that this is bulky group. So now we can see that this bulky group is in between, that between two lone pair, which lone pair is occupying less space. So this CH3 is feeling less repulsion, steric hindrance. Steric hindrance it is facing less, because here both are lone pair, and lone pair are occupying less space. So this is called maximum gauche. Maximum gauche means this is maximum stable. Like there we discuss NT is more stable. Next, after that, here you can see this CH3 is in between bond pair and lone pair. Lone pair occupy less space, but bond pair occupy more space. So it having some strain. Similarly, here also this CH3 is in between bond pair and lone pair. So here this both are relatively less stable. But yes, overall these three are stable. In that this is maximum gauche, means maximum stable. So total number of stable conformers 3. Similarly here also, so that this single bond also will show conformer, this one also and this one also. So let's suppose this oxygen again keeping fixed, here also lone pair and hydrogen. Now that back carbon having CH3 and H. So CH3 again, this carbon should be staggered and this carbon should be staggered. With respect to staggered, now this one is front and back system. With respect to that, this is. It's not like that we are just managing this one and this will be eclipse and this will be eclipse, then it will be stable. No, that will be relatively stable, but we have to do that most stable or that relatively stable conformers. So here, that from our side we will try our best to find out stable conformers. In that, one will be maximum gauche, 1 or 2. So let's suppose here that oxygen front, so it's 2 lone pair and hydrogen. Now back carbon, this one having CH3 and H. Then after again 120 degree we will rotate and 120 degree will rotate. So here you can see one CH3 at least present between 2 lone pair, means hindrance is less, so it is relatively more stable. Means these two are maximum gauge and this is not maximum gauge, but yes, this all three are stable. In that, of course, again I am telling that this back carbon and this carbon is here staggered, here this one is also staggered. Along with that, this representation is the one stable one. Similarly here also and here also, but in this one is more stable, so total conformer is 3. Next, here it is asking for this representation. For this representation isomer, find out all the possible P and Q. So let's suppose this is the front carbon, means this conformer, for that P and Q, what it will be. So here let's suppose this is front carbon, so front carbon having CH3, H and along with P, and back carbon having hydrogen and Q. So molecular formula is given for this C6H14, and with respect to this molecular formula for this given conformer, we have to tell what are the possible P and Q. So let's suppose first linear chain. So by linear chain, this is the 6 carbon. In that, front carbon and back carbon we have to check accordingly. Front carbon should have CH3 and H. So yes, this front carbon having CH3 and H, and so one extra is P is also hydrogen, and back carbon should have hydrogen. So yes, it having hydrogen. So this one propyl will be Q. So this one is one possible in this linear chain. If we will take this one as a front carbon, so it will have hydrogen and ethyl. No, it is not possible. So in linear chain, only one possible conformer is valid. So P will be here, hydrogen, and Q will be here, propyl. Now moving to this one, branch. So 5 carbon main chain and one branching at 2. So now front carbon will be, if suppose this is the front carbon, so here it having CH3 and hydrogen, so this will be Q, and back carbon should have hydrogen. So 2 hydrogen there, so one more hydrogen, so Q will be hydrogen. So this is one possibility. One is that we can set this, we can take this one as a front and back, and another we can take this one as a front and back. Means in that total 3 possible conformer with respect to given conformer in question. Again, if it is at 3 position, then only one conformer possible, and if it is 4 membered, and in 4 membered if both are at 2, then it is not possible. You can check, because already condition is that front carbon should have CH3 and H and back carbon should have hydrogen and hydrogen. So only P and Q If it will be different, we can consider. So here it is not possible altogether. Here we can see that front carbon, if we are taking this one, so it having hydrogen and CH3. So back carbon will be this isopropyl, and this one not back carbon, means another one will be P will be isopropyl, and back carbon having two hydrogen, so another one also will be hydrogen. So either we can take this one as a set, or we can take this one as a set, both are same. So total how many conformer? 1 here, 3 here, 1 here, 4 here, not possible, so here 1. So total how many here? Total we can see that 1 and 3, 4, 4 and 1, 5 and 1 here, 6. So total 6 possible with respect to this representation, where front carbon should have CH3 and H mandatory, and back carbon having hydrogen and hydrogen mandatory. Only P and Q will be different with respect to this given formula C6H40. Clear? So now after this we will discuss dipole moment of given compounds. Like suppose for example this given compounds, so it is polar or non-polar. So carbon and chlorine, in that chlorine is more electronegative, chlorine is more electronegative, so both are cancelling each other, mu 0. This one very important. If it is OH, SH, any lone pair containing atom or group of atom is there, be very careful. Generally we will think that here dipole moment is this side, its dipole moment is this side, both are cancelling. No, it having lone pair also, two lone pair. So let's suppose one lone pair we can represent in plane, one lone pair is there below, means below the plane, we cannot represent that one. So let's suppose one lone pair is here and this lone pair is here. So lone pair also having dipole moment away, lone pair also having dipole moment away from the atom, away from the atom. So this dipole moment is not cancelled. Another possibility, since it can do flipping, means it can do conformers. So if it will rotate, so let's suppose this side one lone pair and this will be this side. So due to that it will cancel. So this one is mu will be 0, but this mu is not 0. So overall can we say that mu is not 0, because overall it is doing flipping. So that one flipping is 0, but another flipping is not 0. So overall this is polar. Similarly coming to here cyanide. So cyanide we know that linear group of atoms, cyanide. So its dipole moment here, its dipole moment here, cancelling each other, it is non-polar. Similarly like OH, this is SH, it also having lone pair, so it is also non-polar. Coming to here that chlorine, so this chlorine, carbon and chlorine, dipole moment this side, and this dipole moment this side, and its dipole moment, its angle will be that its resultant will be here, both will be cancelled. So overall it is also non-polar. Similarly here NO2, so NO2, it's resonating hybrid, through that we can calculate its dipole moment. Here also its resonance hybrid, so both dipole moment cancelling each other, yes it is 0. Now coming to carboxylic acid, yes important. So you can see carboxylic acid double bond and this double bond. Similarly we can consider this carbon and oxygen also bond. So let's suppose we are considering only one. So its dipole moment and its dipole moment not cancelling each other, and it can also do rotation. So if it will rotate, so it will be anti also. So this one is non-polar, but this one is polar. So overall it is polar, because it is always will be in equilibrium due to its rotation. Now coming to here fumaric. So fumaric, in that what is this carboxylic acid here and this carboxylic acid, so its dipole moment will be this side and this dipole moment will be this side. In that carbon double bond oxygen and OH, so it will be not 0, means it's not symmetrical, because here double bond and OH, again here also double bond OH, so it is non-polar. Coming to here, in this case again hybrid, its dipole moment cancelling each other, hence it is non-polar. So this is all about. Now we will discuss in conformer part 2, where we will study that. Till now we have studied that when that two atoms across single bond, it is rotating because of activation energy or surrounding energy is more than its rotational energy barrier. Now we will see after this in ring also do conformers, but they cannot rotate because they are ring, but their flange will flip, especially that six membered cyclohexane. We will see their flanges will flip, and due to that flipping it will also form different conformers. So that we will discuss in part 2. Thank you very much.